Hello everyone and welcome to another video. In this video we'll move on to section 1.2, which is going to be all about the definite integral, and we'll also talk a little bit about areas again. First, I'm going to start off with the formal definition of a definite integral. So there's two types of integral, definite integrals and indefinite integrals. So for a definite integral, if f of x is a function defined on an interval a comma b, the definite integral of f from a to b is given by, right, we already saw this, I introduced this earlier, right, the elongated s is the integral symbol, and then we put the bounds of our interval, and then we have our function, and then we have dx. And then remember, how did we define the integral? We said that the integral is the area under the curve. And what we did was, in our very last video, we said that the more rectangles we have, the more accurate the approximation. So the most accurate approximation in how to actually estimate the area would be to take the limit as you make the number of rectangles go to infinity, right? So this symbol here might be unfamiliar. I'll talk about that in a second. So we take the heights. Remember, the heights is always when we plug in x into f so that we get the y value, and then we multiply that by the width, right? So remember that this is the area of a rectangle with height f of xi and width delta x. So let's talk about this symbol right here, right? So this symbol is called sigma, and it's a Greek letter that we use in mathematics, and this means the sum. So remember that the sum is when you add things together. So remember what we did was we took a bunch of different rectangles and we added their areas together. So that's what this whole entire notation means here, that we're adding together areas of rectangles, right? And then when you look at I equals to 1 to n, right, that just means that when you see we have this index here, I, that means that I want to plug in all of the x's, right? Let's say that we're working with this. So let's call this x1, x2, x3, x4, right? So that I is basically that little subscript there, and we're going to include as many x's as many rectangles we have, right? Because remember, n is the number of rectangles. So basically, this whole notation just means that, right, this means that we want to add up all of the areas of all of the rectangles that we use to split up the area under the curve. Okie dokie. So let's keep going. There's a couple of vocabulary words that I've used that I haven't explicitly defined, so that's what we're going to do. So we define the definite integral, and then if this limit exists, the function f of x is said to be an integrable function. So remember, in calculus, right, so an integrable function, that is a vocabulary word. Remember that in calculus 1, right, not every function had a derivative, right? There were some functions that were not differentiable. So this is the same analogous concept here, right? Where most of the examples we work with, they will be integrable, right? Because we want to get practice taking integrals. However, technically, only if this limit exists is when the integral exists. So 2 key notes is that a definite integral is a number. That is what you're going to get as your answer, right? Remember, a definite integral is the area under the curve defined like this, right? And so then the difference between that and an indefinite integral, right, is that an indefinite integral is a family of functions, right? So remember that in calculus 1, I always like to make analogies to calculus 1 so that you realize, like, all of this stuff is analogous, right? So in calculus 1, we could do the derivative at a point, and we could do the derivative function, which would let us get the derivative at any point, right? Like, we could plug in after we have the derivative function. So for example, if we're given f of x is x squared, we know its derivative function is 2x, and that's true for any x. But we could have asked for the derivative at 2, and that would have been 4, right? So this is the derivative at a point versus derivative function, right? So as you can see that this is a function that you can apply for any x. Similarly, an indefinite integral will be a family of functions where you could plug in lower and upper bounds in there if you wanted to, versus with the definite integral, you always get a number out the same way you would always get a number out for the derivative at a point. And remember, the definite integral is the area under the curve. Okay, and that'll all make sense once we start going into the integral formula, sorry. Okay, so then for notation, this is the symbol for integration, right? That is an elongated S. And then, right, so for definite integrals, on a definite integral, above and below the elongated S are the boundaries of the interval a comma b, right? That's how I've been drawing them, right? Like up here, right? On, we have that a and b. So that is for a definite integral, right? So we would see it like this. And then the numbers, I mentioned this briefly in the first video, the numbers a and b, right? Those are our x values, right? Those are always the bounds of our x values, and they're called the limits of integration. Right, and so a is the lower limit, and b is the upper limit. Okay, so these are all vocabularies, words, limits of integration, lower limit, upper limit. All right. So then just a couple more vocabulary words. We're going to define the integrand. So pretty much just the function that you're going to take the integral of, right? Which in this case here's f of x, right? So we call the function f of x the integrand, and the dx, right, this part right here, indicates that f of x is a function with respect to x, right? So that means that x is the variable in the function f, and that is called the variable of integration. Right, so we can really, it doesn't have to be x, it does not have to be x. So note that you can use any letter as the variable of integration. Right, so what we have here, the integral from a to b of f of x dx, that is equivalent to, right, if we have the same function f, but instead of using x's, we use t's, right, we just have to make sure we also integrate with respect to t, right, or same thing with u's, right, any letter, literally any letter. Okay, so we got variable of integration. Okay, so we have a lot of new vocabulary words, so that's good. So just one important theorem, that all continuous functions are integrable if f of x is continuous on a comma b, then f is integrable on a comma b. And do you remember what continuity means? Right, the simple intuitive definition of continuity that you learn in calculus 1 is that a function is continuous if you can draw it without taking your pencil off of the paper, right? So there's no gaps, no jumps, nothing like that. So all continuous functions are integrable, which is nice. Okay, so I think that the next thing I want to talk about is just some properties of the definite integral. All right, so this is a theorem. Okay, so properties of the definite integral. So the first property, I don't like how that looks. If the limits of integration, and that was a vocabulary word, so go back if you forgot what the limits are the same, then the integral is 0, right? Because you're not moving anywhere, right? If we draw the graph, it'll just be a line, so there's no area for a line, right? So if they're the same, the limits of integration, right here, they're both a or any number. If a was any number, if it's the same, then the integral is equal to 0, right? Because it didn't move, so there's no area to be calculated. 2, if the limits of integration are reversed, then a negative sign is pulled in front of the integral. Right, so let's say I have this function f of x that I'm integrating from a to b, right? What I could do, if for some reason it was easier for me to flip the bounds, right, and make the lower bound b and the upper bound a, then I would have to put this negative sign up front. So whenever you want to flip or reverse the limits of integration, you have to pull out a negative sign. And then 3, the integral of a sum is the sum of the integrals. Right, so if you have the integral from a to b of f of x plus g of x, then you can split that up into 2 integrals, right, each with one function, and add them up. Let me do an example showing you this. So example would be if I'm given the integral from 0 to 1 of x squared plus, let's say, square root x dx, right? Then I can split this up. I have to make sure I keep the bounds the same, so I take the first function and integrate that, and then I take the second function and integrate that. So basically this is telling us, like, we can go term by term. If they're all added together, we can, like, if we have, for example, like a polynomial, let's say x cubed plus 2x squared plus 6x dx. The same way we could go term by term to do, if we wanted to do a derivative of these, we could go term by term to do the integral, right? So we can just do the integral of the first term plus the integral of the second term plus the integral of the third term. Okay. And the same thing is true when you have a difference, right? So when it's subtraction, the same thing holds. So the integral of a difference is the difference of the integrals. Right, so it's just literally the same exact idea that we just went over for addition. So I'm only going to write the generic rule here, right? So if we have a subtraction sign in between 2 terms, then we can split up the integral over that subtraction sign. So as long as we keep our bounds the same, that should be a g of x. Alrighty, and this one I love is that we get to pull out constant multiples. Is the key word, right? You don't get to just pull out, let's say for example, if this was just a 6 added on here, I wouldn't be able to just erase this integral piece and just add 6, pull out the add 6. No, that would be wrong. You would have to still integrate 6. However, if it's a constant multiplied, right, so let's say if we were given the integral from a to b of some constant c times some function f of x, right, then we could pull the c out in front of the integral, right? So for an example, if we were doing the integral from 0 to 1 of 2x squared from above, what we can do is just pull out the 2 in front of the integral and then just integrate x squared. And then after that, I would multiply it by 2. All right, we're almost done. This one is nice. 6 says that if you have an integral from a to b of f of x, you can split that interval up with some number in between a and b. So in this case, we're going to call it c, right? And then you add on the second part. So this makes sense if you think about like a graph. Like let's say that our function, this was our function, f of x, and then this is a, and this is b, right? And then there's some c in between, right? Either I could do the area from a to b and not think about c, or I could break it up into 2 areas, right? And then just add these together, right? So this is pretty much our A1 part, and this would be like our A2 part. Okay. We just have a few more. So let's see. If some function is always greater than another function for all of the x values in a specific interval, then we can also expect the integral of the greater function to be bigger, which makes sense, right? Because we know how the integral looks graphically. And I think that's all I want to go over for today for this video. So hopefully that wasn't too much. See you guys in the next one.